Good afternoon. I would like to thank the Remai Group for the opportunity today to present to you the research I did as part of my conservation degree course at City and Guilds of London Art School. I must say I'm rather humbled yet very excited to be sitting here today in front of various experts in Islamic art. My research, however, was not based on Islamic art, but in plaster casts in the Victoria and Albert Museum cast collection. Both these objects consist of a form of gypsum plaster, a soft and brittle material which requires special consideration before conservation. I hope that my talk today will highlight some of the considerations to be taken and provide guidelines for conservators with not only plaster casts, but also other artifacts consisting of calcium sulfate. The Victoria and Albert Museum has an impressive collection of plaster casts. Part of this collection had been in storage and not seen by the public for a considerable amount of time. Amongst these was a small group of casts taken from Westminster Abbey by the firm of Bruciani & Co. in 1868. They needed cleaning to go on display in the V&A's new medieval and Renaissance galleries. One of these figures, this is the mouse showing there, that figure over there, is a cast of St. John the Evangelist, and this was used as a model to study and to find the most suitable cleaning techniques which could be then applied to the rest of the group. Plaster of Paris derives from the mineral gypsum. When we talk about plaster of Paris, we refer to a purer and more refined form of gypsum plaster, more than that used in antiquity, and produced by modern manufacturing methods. This commonly used term originated from the fact that gypsum has been mined from the hills of the Parisian suburb of Montmartre since Roman times. Gypsum consists of calcium sulfate, which occurs in three forms in nature: dihydrate, hemihydrate, and anhydrate. By adding heat to calcium sulfate dihydrate, a chemical reaction occurs, and 1.5 molecules of water are driven off, leaving calcium sulfate hemihydrate. It is at this stage when they crush and pulverize the rock to form the powdered form of gypsum plaster that we know. Then in reverse, if you add water to the hemihydrate, it combines with water molecules to form dihydrate crystals, which grow until they interfere with each other and cannot move around freely anymore, forming a crystal matrix, the set form of plaster of Paris. The properties of plaster of Paris, which make it such a wonderfully useful material for both artist and conservator, also means that it makes it quite a very problematic material to conserve. This is due to its porosity, water solubility, and brittleness. The formatori were well aware of the weaknesses of plaster of Paris and often used additives within the plaster mix for strength or applied coatings to the surface for protection. They also added accelerators or retarders to the plaster mix depending on the size or amount of cast they were producing and whether they needed to hasten or slow the set of the plaster. The custodians of plaster casts were also aware of the weaknesses of plaster, and they too often applied coatings for further protection of casts after they came into their care. It is safe to assume that it is quite uncommon for casts in a collection such as this one not to have anything applied to it, with more than one coating often applied at the point of manufacture. This needs careful consideration, as not only does it influence the decision of what level to clean to, but also what method of cleaning should be used. For example, milk was often used on plaster casts that were taken from marble sculptures to create a marble finish. This would mean that it would be an unsuitable, using the ND YAG laser would be an unsuitable method to clean a plaster cast that's been treated in that way, as casein will darken when exposed to the laser. Frank Forrest Frederick's 1899 publication was a valuable source describing plaster manufacturing processes as well as casting techniques employed during the 19th century. It was published in America 31 years after the Bruciani casts were produced and mentions Bruciani & Co. as a source for obtaining quality plaster casts. Frederick's priority in applying treatments was for an aesthetic finish rather than damage prevention, and any such beneficial outcomes were considered an added bonus. He describes the oiling of casts with linseed oil to be the most desirable treatment to apply, as it has a threefold purpose. It creates a very satisfactory tint, hardens the plaster, and makes it impervious to water. He, however, does caution against the heterogeneous nature of plaster, as successive coats of oil will darken porous areas, making the cast appear patchy. Half a century later, Jack C. Rich, in his book, The Materials and Methods of Sculpture, is more concerned with the strength and the future condition of casts. He describes oil as not being as desirable as wax or shellac treatments, as with time it oxidizes and discolors. The group of casts came into the collection shortly after manufacture in 1868. Their current condition resulted entirely from environmental conditions within the museum's storage facilities since that time. A letter from the 28th of April 1932 to the assistant manager of casts at the time names less than ideal storage locations for casts and moldings, including showroom, packing room, workshop, basement, cellar room, known as Clincher's Hole, chamber of boiler room, tin hut by the old building of the Science Museum. There are two references to casts located in the upper galleries, one from 1888, noting that Brucihani had been given authorization to stamp casts in the upper galleries to be reproduced and sold. The second note more specifically refers to casts being waterproofed and stored in the upper galleries of the architectural courts today known as the cast court. So that note is evidence as well of casts being treated once they are in the care of the museum. The cast court is a vast space, and environmental control is difficult. Today, the environment is carefully monitored and controlled, but it was certainly not the case in the 19th century. Any liquid or moisture in the air could act as vehicles for dirt that has settled on the surface to be carried deep into the pores by capillary action. In the past, there were also not modern systems in place for preventing external pollutants, such as dust and smoke entering the museum. But there was a growing awareness of harmful effects of pollutants to artwork by the mid-19th century. Eastlake, the keeper of the National Gallery in 1848, once described his attempt to settle dust in the National Gallery by watering the floor occasionally. He and Faraday in 1850 compiled a report on effects of pollutants on artworks for the National Gallery. Faraday differentiates between different types of pollution: inorganic fumes from chimneys and the organic miasma from the crowds that are in the town. The pollution in London reached critical levels before action was taken to prove it by passing the Clean Air Act of 1956. Museum dirt or unwanted deposits on objects within museums since this time include handling dirt and dust consisting of fine particles of textile soot, silica, salt, and salt crystals. Particles produced from burning fuels, which are tarry, sooty, also acidic, as they absorb sulfur dioxide. Harmful gases that have been present within museums are sulfur dioxide, nitrogen dioxide, and ozone. A combination of museum dirt and moisture, either from condensation, damp, storage, or even a leaking roof, has altered the surface of the sculpture significantly in areas. Plaster of Paris is soluble in water. This, as well as acidic conditions created by pollution, have etched the surface of the plaster around the shoulders. A clear line following the profile of the head is seen on the chest. The plaster below this line has been rinsed clean, but above this line the plaster is coarser, darker, and the surface more etched, as dust has settled and adhered, protected by the face. The dirt has had time to react with moisture, making it acidic and etch the surface. The left side of the forehead has also been washed clean, and there are vertical lines running down the side of the cheek. The cast surface varies in color from a black soot-type dirt, yellow staining, orange-brown coated areas to white, clean areas. There is also a crusty brown layer, which is harder than the substrate and which has delaminated in areas. Now, a very useful way to quickly assess whether there are one or more coatings on a plaster cast is using a strip of plaster of Paris, where I applied many treatments which were commonly applied to casts in the 19th century, and then compared them to the plaster cast under UV light. It showed that there was at least 2 different coatings on the plaster cast. A green fluorescing layer followed by an orange fluorescing layer. The closest match to the green was beeswax, gum arabic, and rabbit skin. It has to be taken into consideration that the age, concentrations, and number of applications of the coatings tested could differ from that applied to the cast, resulting in a difference in the intensity of their fluorescing. A cross-section was then made to confirm what I found with the UV. A cross-section was made of a sample taken from an area on the cast with a yellow staining. Observation under magnification 20 revealed how far the staining had penetrated below the surface. In order to identify the staining material, a protein and oil test was done. The results indicated the presence of protein on the surface of the cast, but not of oil. Neither of the tests affected the deep yellow staining underneath the surface. Unfortunately, I did not have the facilities to view the cross-section under ultraviolet light, which would have helped to identify whether the staining was shellac. I understand that the V&A Science Department are currently doing more thorough and advanced scientific analysis of the surfaces of some of their casts, and I'm eagerly waiting the results of that study. It is impossible to recreate the exact surface conditions of an old cast, as many agents of deterioration have had time to react. However, with a clearer idea of the type of dirt and the possible coatings to be found on the surface, artificially soiled plaster of Paris samples were prepared to avoid damage to the V&A cast and for ease of analysis. Modern gypsum plaster was used as, according to Frederick's manual, manufacturing kilns during the 19th century much resembled the modern kilns employed today. Two of the samples were coated in treatments thought present on the cast to see the effect of cleaning methods on them. These were a beeswax and turpentine mix and rabbit skin glue. Both samples were then half coated with shellac. One sample was left untreated to see the effect of the cleaning methods on bare plaster. The most effective cleaning method was then judged visually. Damage to the plaster surface of the effective methods were analyzed under an optical microscope. The cleaning methods found to be the most effective yet least damaging were then chosen for the next phase of the experiment, where further analysis was done using white light interferometry on pure plaster control subjected to the chosen cleaning methods. This is just an example to show my method where I did the cleaning tests on the artificially soiled samples to see which ones were most effective and also to see what effect they had on the treatments applied. And then underneath is where I chose the most effective methods and then viewed them under an optical microscope to see the damage to the surface of the plaster. This is an example of the results of the visual analysis of the clean effect of dry cleaning methods and the analysis of the surface damage under an optical microscope magnification 40. Note how it appears that all the dry cleaning methods had an abrasive effect on the plaster controllers, showing the vulnerability of an untreated plaster surface. Any mechanical action appears to significantly abrade the surface. This also proves the protection offered by coatings applied. This slide shows the effect of the surface after cleaning with ND-YAG laser. Note that the superficial dirt was removed, but that staining or discoloration remained. The next 4 slides will show the results of analysis of plaster controls before and after surface analysis with white light interferometry. The examples I have chosen to represent here are the 2 methods which most and least altered the surface roughness. This slide shows the results before cleaning with 3% Laponite and 3% fumed silica applied over wet alkaline tissue and lifted off. This is after the cleaning, showing the difference in surface roughness. The next 2 slides show the insignificant difference of 0.438 microns before and after laser cleaning. The graph indicates the difference in surface roughness before and after each method of cleaning. I will now discuss each of the cleaning methods tested briefly and the results obtained. Dry methods are safe chemically and no unexpected chemical reactions occurred upon the surface. Visual analysis appeared to show that all dry cleaning methods altered the surface of untreated plaster casts. The test did reveal that surfaces treated with shellac and wax offered some protection against abrasion as they formed a thin film on the surface. Plaster of Paris is insoluble in mild organic solvents, but because of the porous nature of gypsum plaster, solvents pose a risk as they will dissolve what is on the surface and this solution will be absorbed deeper into the plaster. It is not advisable to use solvents on plaster, but it has been used by conservators in the past. With caution, using a controlled amount of solvent on tightly rolled swabs with very little pressure applied swiftly before the coating has had a chance to be absorbed. As plaster of Paris is soluble in water, a method was often used where white spirit is applied as a barrier coat, filling the intercrystalline spaces, preventing further absorption when cleaning with deionized water. The white spirit was applied with a soft paintbrush before swabbing with water. This method was included in the solvent tests. On coated samples, ammonia, as well as the white spirit and deionized water, worked well. They did, however, notably erode the surface of the uncoated samples. All solvents tested on untreated samples etched the surface to an extent as a combined result of solvents softening the plaster and the mechanical action of swabbing. Solvents work well on the treated samples, particularly on areas with shellac. The removal of shellac from plaster casts is, however, complicated. Practically, solvents risk shellac being further absorbed, and solvent gels may leave a residue. And ethically, if it is an original treatment, should it be removed? And does the coating only remain in patches which have discolored, thereby interfering in the way you read the work? Latex poulticing. The latex products tested was Arte Mundet and Anchusil. Arte Mundet Type 1 is a peelable poultice based on a natural rubber latex and ammonium hydroxide dispersion with a pH 9. It has a cream coloring and can be applied by brush, roller, or sprayed. Drying time will vary according to the thickness of application, relative humidity, and temperature. It was applied by brush to a thickness of 2 to 3 millimeters. There are 3 types of Arte Mundet, with type 2 and 3 both containing EDTA, a chelating agent which sequesters calcium and iron. For this reason, it was considered safer to use type 1. Anchusil is a new product developed by the conservation company Restaura Albayalde, based in Madrid, Spain. It is based on a natural rubber latex, plus minus 90%, with water, ammonia, methylene chloride, and surfactants added. It has a lower viscosity than Arte Mundet, a pH 7, and has a blue coloring. It is applied by paintbrush, and the working time varies between 20 and 30 minutes. Anchusil was applied with a brush in the same location and conditions as Arte Mundet. Because of its low viscosity, it was easier to apply as the Arte Mundet and resulted in a thinner coating. This in turn caused a faster drying time, and the Anchusil started to dry after 5 minutes and was dry completely after 3 hours. Both products were applied in a room with 40% relative humidity at 20 degrees Celsius. Both products cleaned well after 2 applications on the uncoated samples, the first application removing surface dirt and the second application removing some staining. It was, however, not that effective on treated samples as a result of the pores being blocked by treatments. Arte Mundet cleaned to a greater extent than the Anchusil, but the Anchusil had a much faster curing time and was easier to use. A gentler clean also meant cleaning could be controlled more. Laponite is a synthetic clay which is often used in stone conservation as a poultice. After consulting various conservators and researchers about Laponite methods, I realized that this poultice is used in various concentrations and in various ways, such as being applied directly or over wet alkaline tissue, with or without fumed silica added, and sometimes it's left, some conservators leave it to dry and then brush it off after it started flaking, where others prefer to apply it over wet alkaline tissue and lifting the tissue off. The pH of Laponite is between 8 to 9, and citric acid can be added to neutralize it. All samples were applied to a thickness of 2 to 3 millimeters and removed after 1.5 hours. Of the Laponite poulticing method, the most successful concentration was 4% Laponite with 4% fumed silica, applied directly and left to dry before brushing off lightly. It appears that both pre-wetting with tissue and swabbing etched the surface of the plaster significantly. It is interesting to note that the most damaging was the 3% Laponite fumed silica applied over wet alteoline tissue and then removed by lifting the tissue off. This could be due to the more moisture contact as a result of lower percentage of Laponite combined with the moisture from the wet alteoline tissue. Tests were done on all samples with a Q-switch ND YAG laser using the same parameters for wavelengths 1064 nanometers and 532 nanometers. Affluence of 0.03 joules per centimeter squared was not effective and 0.8 joules per centimeter squared pitted the surface. As just mentioned, plaster casts are not homogeneous. Not only do the plaster differ from cast to cast, but also areas within casts can differ in density. The test done on the samples gave interesting results. It cleaned the surface soiling, but not staining. In order to remove the staining, the laser will have to ablate the substrate, which would be detrimental. The laser was tested on samples with a range of treatments applied to see whether any chemical changes occur. Very interesting results were obtained, including on the untreated plaster of Paris sample. The plaster had a slight green hue. The wavelengths 532 nanometers resulted in the strongest color change, and on the treated plaster samples treated with milk and beeswax, the hue was most intense. This is a new phenomenon and will have to be investigated further. This is a case study where Sophia Marquez from the Victoria and Albert Museum applied the knowledge gained from the research. This was on a, almost there. St. Stephen was one of the casts selected for display from the Westminster Abbey group. It had a similar surface condition to that of the cast in the study and was conserved by Sophia Marquez. Sophia successfully used a combination of anchusil and laser to clean the casts. The entire surface was cleaned first using a latex poultice. Anchusil, applying it with a soft paintbrush, she covered quite large areas simultaneously. The anchusil dried in less than 3 hours, and she applied successive applications as she required them. On areas where there was a thick black layer not affected by the anchusil, and where the plaster was too friable to use a poultice as a result of environmental conditions, she cleaned using a laser with an infrared wavelength of 1064 nanometers. She did cleaning tests and under visual observation found no discoloration of the plaster. And so just to conclude, of all the tests done, the cleaning methods that best fit the criteria was the latex poultices, as the effect on the texture of the surface of the cast was marginal. They also did not chemically react with any treatments applied. Neither were they abrasive as dry cleaning methods or solvent swabbing. Most importantly, they contain a negligible amount of water. The ND-YAG laser cleaning showed the least alteration to surface roughness, but on test samples there was a slight color change. In a separate investigation on an aged plaster cast at City and Guilds of London Art School, the laser successfully removed surface dirt used at a fluency of 0.15 joules centimeter squared at a wavelength of 1064 nanometers. It did, however, leave a yellow-brown staining similar to that seen on the soiled samples. The wavelength, 532 nanometers, appeared safe, but further testing should be done. All dry cleaning methods altered the surface, with the least damaging method being the smoke sponge. This, however, did not clean very well either. Any wet cleaning, solvent or Laponite, are not suitable, as all tested significantly altered the surface roughness. Frederick mentions that every formatore possessed a secret recipe to let the plaster behave in a desired way. Despite this, plaster is also not homogeneous, and one area of the cast will differ from another in density, strength, condition, and surface applications, and therefore often requires a combination of methods. It is important to never make assumptions and to be diligent and to do cleaning tests before proceeding cautiously. Thank you.